Welcome back to ECE 441A, 541A. Today is the date for your passports to be finished up, so make sure and get those put in. I looked on D2L, and I don't know if it was this class or my other class, but I had the date wrong on D2L. I've been telling you it's Monday, but on one of the classes I actually had the due date in the Dropbox listed as tomorrow. If you are planning on doing it tomorrow, go ahead and submit it tomorrow, but I have corrected that due date, and I think we're now scheduled for it to be due today consistently across all the different modes of communication. I would like you to take the pre-quiz. I think yesterday I noticed about half of you have, maybe more than half, had turned in their passports. I didn't check on the pre-quiz. Not sure how many of you are brave enough to have completed that, but it's not that big of a deal. And homework number 1 is due, is that in a couple of weeks? I think it is. So the 10th of September is a couple of weeks. A week from today, you won't be, well, you can come. I don't know if the doors will be open or not, but a week from today is Labor Day holiday, and you won't have class scheduled. I'm not planning to be in this classroom in a week. What I want to do is many different things. The main thing is listed in really item 2, but first someone came up after class and said, can I practice creating state space representations? Show of hands, how many practiced all weekend creating state space representations from circuits, from mechanical systems? Oh, is all weekend the equivalent to 5 to 10 minutes? I'm not sure that I would agree with that equivalence, but at least you tried. So I'm going to give you credit for spending 5 or 10 minutes, but I would recommend that you spend a little bit more time than that trying to understand how do we create these state space representations. It will be probably on the exam from a circuit or a mechanical system, etc. Today, what I want to do is try to understand how we can find this transfer function for this particular system, our mass spring damper system, many different ways. You'll do it through Laplace transforming the differential equation. That's dE. The transfer function is TF. The block diagram is BD, and the state space representation is SS. I'm giving you all of these acronyms so that when you're texting to mom or dad, you can just include the jargon, and I'm sure they will know that you're doing a TF to SS or a SS to TF transformation, and they'll know exactly what you're talking about. But that's what we're going to do today, is a differential equation, a dE to TF, a block diagram to transfer function, and a state space to transfer function. We'll then think about what the Bode plot of these so here's the answer in the back of the book. Those 3 strategies for finding the transfer function better give us the same G of S. We may start with 50 different state space representations of the same system, but they all should give you the same transfer function. That's a way to check your work. Meaning, if you're now finding a state space representation and your buddy finds a state space representation and they're different, you might say, well, let's check them. Let's find the transfer function. If you get the same transfer function, you're pretty assured that you do have equivalent meaning they model the same system, state space representation. Then we will move into developing the equations of motion for something more than a single mass, a 3-mass system. And what does that look like? To get you started thinking about that, here is the next step, let's say, in that transition of creating a state space representation. If you spent 5 to 10 minutes doing it this weekend, now you can spend 15 or 20 minutes later today doing it for these cases. I have N cases, Nevada cases, that I'm going to scroll through real quickly. N is, it's finite, but I don't know what that represents, that N. Nobody's awake yet, so that didn't mean anything. But this particular system should be very similar to what we've already done. How could you make this system look just like the system we've already sketched or worked on? Pardon? Hold mass 2's position fixed. How could we do that? Besides trying to grab it, we could let it go to infinity, couldn't we? We could just let it be an unmovable mass. So looking at extremes sometimes is helpful. When we're looking at something new, sometimes it's nice to try to connect it with what you've already done. You can now connect this system with what we've already done by saying, oh, let me let M2 go to infinity. And now you have that right end of the spring connected to a solid immovable object, or that brick wall that I had indicated in earlier examples. And so if you develop the equations that govern this system and let the second mass go to infinity, that should bring you back to what you had before. What would happen if you would let M2 take the other extreme and go to 0? You have an unattached spring, and what's that going to do? Nothing really, except in our case it's not even going to add mass, but in reality it might add a little mass to M sub 1, but it's not changing the general idea or structure of the dynamic behavior. In this particular system, how many state variables would you expect to have? Vote on your table, and then when I say at the count of 3, I want your table, some representative of your table, to show me fingers. So I'm basically saying that the state variables represent something that can be represented by one hand. So you need to have an arm representing your table. And if you're at home, you can just raise your finger at the count of 3, or fingers. Is your table, have you reached consensus at your table? It shouldn't take you too long. We're getting ready for tomorrow. The primaries are tomorrow, so we're going to vote today in this class. We ready to vote? At the count of 3, I want you to show me your fingers, and not before I count to 3. I don't want other people being influenced by your vote. Ready? 1, 2, 3. I see some non-voting tables, and I wanted one hand for each table. You're supposed to reach consensus. Okay, I see some 3s. I saw a 6. I saw 4. I'm not seeing anything on my west side of the classroom. Is that the correct direction? I hope I'm oriented correctly. I see some 3s. How do we find the number of masses in this system? Masses. How many masses are there? How awake are we? 2, right? So how many state variables? That's influenced by the variables of interest. How would you define variables of interest for this system? What variables are interesting? None. And that's not an allowed answer, especially on the exam. You can't say none, or I'm not applicable. Well, we always have this guy that we can fall back on. We've already done that. We need its position and velocity. And can't we do the same thing for the second mass? If we called its position, we draw a line in the sand and we say, okay, here's z sub 2 and z sub 2 prime. How many variables does that represent? 4. That's the number of state variables we would be expecting from this particular system. Case 1. Again, we have n of these cases. Here's another case. Case 2. A little differently. It is allowed that you can actually have dash pots and springs in between the same masses. That's okay. You could have them connected sort of in series if you wanted as well. That would be a different interconnection strategy. But now, what are your variables of interest for this mass spring damper system? And when you're looking at this, you want to be asking, how many, if I fixed everything but one point of interest, how many points of interest do I have? In this case, what if I fix mass 2? What can move? Mass 1. If I fix M1, what can move? Mass 2. If there were a spring and a dash pot connected serially, the massless point between them could maybe move, and then we would have a different variable as well. But here we have exactly the same variables of interest that we had before. So let me label them the same. We have the position and velocity of mass 1, and we have the position and velocity of mass 2. Even though case 1 and case 2 are different, how many state variables are there in case 2? 4. Position, velocity of each mass, and that gives us 4 variables of interest. And if we have 4 variables of interest, 4 variables in our state vector, what does that mean? We want to find what does the first variable's derivative look like in terms of those 4 state variables. What's the second variable's derivative look like? How do we describe it in terms of those 4 state variables and the applied inputs? Do you see that I could also put an input somewhere else? I could have a u sub 1 and a u sub 2 if I wanted to. Would that change what if I applied a u sub 2 there? And here's u sub 1 now. How many state variables do I have? Still 4. How many inputs do I have? 2. What's changed in my state space representation between case 2A and case 2B, if that makes sense? Has the system matrix changed? The A matrix? Dimensionally, no. Internally? We're not that far from the exam, so you want to be kind of following along, I hope, and thinking about what this means. A doesn't change. The system matrix doesn't change. What about the input matrix? It's now widened, hasn't it? It's obtained a second column between case 2A and case 2B. Initially it was 4 by 1. Now it's 4 by 2. Questions on this? And you now can go home. Now I've given you some extra cases to examine, and ... you could just keep going if you wanted to and spend n times 15 minutes deriving those different state space representations. Practice. Let's now look at deriving transfer functions for the mass spring damper system. And here we are. This is the one that should make you just feel warm and fuzzy. This is your teddy bear for the semester. All right? This is the one that you now know. How many have already put this on a 3x5 card and it's under your pillow? Only one wants to admit it. I think there's others that have actually done that. So you could have this on one side of that index card, and you could have this differential equation on the other side. You know how to find that differential equation, and that's in the time domain. How would you find that? How do you find the governing differential equation for this mass spring damper or any mass spring damper system? How did we talk about? Start drawing free body diagrams. And you have a free body diagram for every set of points of interest. In case 1 and 2 earlier, you would have a couple of free body diagrams to worry about. And there, it gets a little more interesting because now, if I scroll back, let me scroll back to case 1. That's not quite as many moving parts or as many things. Do you see that the spring force that is applied to mass 1 depends on both ends of the spring now, not just X or X1. It depends on X or Z sub 1 and Z sub 2. So look at that when you're deriving these equations. When you say, oh, the force from the spring on mass 1, that's now going to be a function of K, the spring constant, and the position of the left side and the right side of that spring. And you need to combine those two variables in such a way that you get a positive force based on the movement of Z1 and Z sub 2. Hint. That's a hint. Where were we? Deriving or reminding ourselves of the differential equation of this original mass spring damper system. What I want you to do now is Laplace transform that and find the transfer function between the input U of S and the output capital X of S. So what I'm looking for now for you in this activity is to find G of S, which is really just the ratio of the, let's just assume that the output in this example is our position of that mass, and the position is X, its Laplace transform is capital X of S, and the input Laplace transform U of S. I want you now to find G of S. And you can use the whiteboards at your desk. Now we have all this technology. We can now take a picture of that with your smartphone, and now you have it. A lot of times I would go, well, now they're not going to have it in their notes. Well, now you have it. You can carry it around. You can text it to mom and dad or whoever, and they'll go, oh, you're doing the mass spring damper system. Do we have an answer? Do we have a G of S? Did you know where to start? What happens when you Laplace transform x double dot or x double prime? You multiply by s squared. So you should have something G of S that looks like, let's say, gamma m s squared plus bs plus k. Did you get that? Or if you made your denominator polynomial monic, is it clear what I mean by that? If your denominator polynomial is monic, that means that you've normalized the leading coefficient to 1. I'm going to factor out m from each term in the denominator and move that m upstairs so that you could maybe see the transfer function written as gamma over m s squared plus b over ms plus k over m. Either of those transfer functions is correct. And if you didn't get that, if you have questions, ask your buddies after class or come see me in office hours and we'll work through those steps. But you should feel comfortable with that being your transfer function. Let's now look at finding the transfer function. So there are the answers in the back of the book. This is what we want to achieve in the next couple of ways of finding the transfer function from the block diagram and the state space representation. So if we don't even get there, you know how to find the answer, or you know the answer. You now need to figure out the steps to get that answer. Let's look at the block diagram. And I think we did this last time. You could find the all-integrator block diagram from the state space representation or from the differential equation. How do you convert the all-integrator block diagram into the frequency domain? You simply replace those integration operations in the time domain with 1 over s's. And your variables now are frequency domain quantities. You now have the Laplace transform of all of your signals in that. And I believe if I just write this down, we had something like gamma over m scaling the input u, and that's now capital U of s. Here is our output x of s, and we had a minus b over m scaling, let's say, x sub 2 of s. And if I don't indicate a sign going into these arrows on the summing junction, you can assume that it's positive. So my sign is now in the gain itself, and we have a minus k over m scaling the position and feeding that back to form the 3 inputs of that summing junction. And if you have one 3x5 card, you probably had to buy it in more than a quantity of 1. Now you have another one that you could put this on the back of your mass spring damper system if you wanted to. You could do the all-integrator block diagram and then this frequency domain block diagram. Has everyone studied block diagram algebra? Did you do that in 340A? Pardon? Really, you're confessing? So I can go to your instructor and read them the riot act? Okay, so now let's find the... we can just do block diagram algebra. You could do Mason's gain formula, but let's label some of these signals. And a lot of times if you're trying to find the, let's say, a transfer function associated with this block diagram, you probably want to start worrying about or thinking about writing your equations in terms of the output signals of summing junctions. Let me say that now I have beta is the output of that summing junction, and going into that I have a signal alpha 1, a signal alpha 2, and a signal alpha 3, so that at that summing junction the relationship that I have is now beta is equal to alpha 1 plus alpha 2 plus alpha 3. That shouldn't surprise you. So we have the output is equal to all the inputs. Now we simply replace those labels with the actual signals in our block diagram. For example, maybe we want to call this W. You can call it whatever you want, but now beta is W, so now I have W of S is equal to, what's alpha 1? That's a signal, and so it can't just be gamma over M. Gamma over M is a number. That's a gain. Alpha 1 has to be a signal, and it can be a signal in the frequency domain by scaling the input U with that gain gamma over M. Alpha sub 1 is then gamma over M U of S. What's alpha sub 2? Did everybody hear that? Minus K over M capital X of S. And alpha sub 3? Is everybody okay with that? Now we need a transfer function, which means we want to find the ratio of X over U, which means we have some extra signals in here we really need to get rid of or rewrite in terms of X's or U's. Now we need to replace W or rewrite it in terms of X or U, and X sub 2 we need to rewrite that in terms of X or U. Is that clear? We just want X's, U's, and variables so that we can now find the ratio of X over U to find the transfer function. If we look at our block diagram, you can see a relationship between those quantities. Do you see that X sub 2 you can now write as W in some way? In the time domain, X sub 2 is just the integral of W, isn't it? So now we know that X sub 2 of S is 1 over S W of S. And you're going, yeah, but that doesn't do me any good. I wanted X's, not X sub 2 and W. Now I'm just throwing the same thing back and forth. But hold on, we know how to find X sub 2 in terms of X from the block diagram. Right? They're just related by this operator 1 over S. We now know that X is 1 over S X sub 2. And we can now put this written as the right-hand side. And now we now know how to replace X sub 2 with an X expression. We can multiply the appropriate way by S. We can just multiply both sides by S. We can also say, oh, we also have 1 over S times 1 over S W, or 1 over S squared W of S is X as well. And now we have the relationships that we need. W of S, anywhere in that original equation, we can replace it with S squared X of S using this relationship. Likewise, what's X sub 2 of S? Or similarly, We want to write it in terms of x. It's just s, x of s. Everybody clear on where those relationships came from? The block diagram. And now we are in a position to replace these troublemakers. W, we can get rid of that or rewrite that in terms of x. That's s squared x. And x sub 2 is s times x. Or now we have s squared x of s is equal to gamma over m u of s minus k over m x of s minus b over m s x of s. And now we are in a position to collect common variables or collect terms, and now we have s squared plus b over ms plus k over m times x of s equaling gamma over m u of s. And you should start to be feeling comfortable with what we're getting. We now have g of s is our transfer function of the system, is the output's Laplace transform divided by the input's Laplace transform. So now we're just doing some cross multiplying, and we end up with gamma over m upstairs and s squared plus b over ms plus k over m. And was that on the back of your 3x5 index card? That's now the answer in the back of the book. Yay! So that should start making you feel good about doing these manipulations. Questions on that? We've now gone from differential equation to state space, block diagram to... No, I'm still asleep. We went from what? Differential equation to transfer function. Now we just went from block diagram to transfer function. We want to do the next step, which is to go state space, SS, to TF. So now we're going to do the state space. And you probably already have this memorized. What did we write this in terms of in our... So I'm going to label the position x sub 1 and the velocity is x sub 2. Does that really confuse you? It should be clear from context what I'm trying to do. And before maybe we labeled the position z and its derivative was the velocity. You can do that if that makes you feel a little bit better. In our state space representation now, we want to find the first derivative of x1 and the first derivative of x sub 2, rewriting those in terms of some linear combination of the state plus some linear combination of the input. And we've done that already. And let me fill in the blanks. We have a 2 by 2 matrix. The interesting structure is in the second row of the A matrix. There's our system matrix. Our input matrix had a 0 top row and a gamma over m bottom or second row. There's our B matrix. And let's just assume, well, that's what we've done in the previous two examples. We let our output be the position of that mass. And our position was simply x sub 1. How do we make that happen for y? If y is x sub 1, how do we create that from this collection of matrix vector products? Do we have u appearing in our output explicitly? No. So that gets a 0. There's our direct feed-through matrix, D. It's nothing. And now what do we want y to equal? That's the position of mass 1, and how did we label that? X1, which allows us now to just pull that off with an output matrix C being 1, 0. And now we can rewrite that as in a compact form. Here's where it might get a little more dicey. This x is now a vector x compared to what we'd called x before. Is that clear? So I'm overusing x. But now x prime of x, which is really x1 prime, x2 prime stacked on top of each other, is a x plus b u, and y is cx, and I could really just quit there, but let me just say plus d u of t. I have the dynamic relationship of my system. That's this x prime equation, and I have the output equation y. Question?
I was confused about, is there a particular reason when you switch from the variable x to z?
So now the question is, why are you confusing us, I think, is the question. I rephrased it. But before, what I had done was I had, to make it easier, well, to make it less confusing, I'd called those z and z prime, which means that down here, this would have been m z double prime, etc., and my transfer function would have been z of s over u of s. I wanted to avoid that in the first two, but now that I have on the third time in the state space, it's getting confusing because now I'm using x as a vector, and in the block diagram it was the position. What? So I hope you'll tolerate the abuse of notation that now I've switched into calling x a vector. And now I want to find x1 prime, x2 prime stacked on top of each other. That's equal to a matrix A times the vector x. Okay? Question? Could I put the little arrow on top? That would be ideal, wouldn't it? But am I going to remember that? Probably not. So the comment, the suggestion was to say, well, now that it's a bar, but if I say bar in a classroom full of college students, what are you going to be thinking? So I usually don't bar things. Sorry. So now we have x bar. Is that better? Maybe. So for now we have x bar, and we have x1 and x sub 2. Is that better? Okay. Where were we? See, we get distracted by that notation. But I'm trying to make it clear. What I want to do now is take it into the frequency domain and find a transfer function. Let's Laplace transform the differential equation. Now we are Laplace transforming vectors. No big deal, we just Laplace transform each component of the vector individually. So what happens when we Laplace transform this dynamic equation? We're Laplace transforming both sides. Have to do the same operation to both. We Laplace transform the left side. That's equal to the Laplace transform of the right side. What helps us out a lot is the fact that these A and B matrices are constant. And so the Laplace operator just slides right through those. And what happens when we Laplace transform a derivative? In general, now, before I'd sort of said, oh, let's throw some of this away. Let's keep it now, just so that we understand what all is happening. What happens when you Laplace transform a derivative? You multiply by s. Do you have anything else following along, tailing along? Initial condition, right? So now we have s times x of s, and that x of s is a vector. It's the Laplace transform of capital X sub 1 and the Laplace transform of x sub 1 of t, which is capital X sub 1 of s, stacked on top of capital X sub 2 of s. And we have minus x of 0 minus. This is time t equals 0 minus. And the initial condition is a vector. So now you're wanting me to bar these, aren't you? See, I told you I would forget. I just get sloppy or lazy. Do I have to bar the capital X? Okay. I'm done with the bar today. It's too early in the morning to worry about bars. Where are we? Oh. Now we need to Laplace transform the right-hand side, which is a times the Laplace transform of x bar of t plus b times the Laplace transform of u of t. But we've already Laplace transformed x bar, haven't we? This is now a, capital X of s, plus b, capital U of s. A lot of times, Laplace transforming, all we have to do is hit the shift key. Capitalize. Now, I want to combine terms in this expression, and right now S is a scalar on the left, and the matrix A is a matrix, 2 by 2 in our case. How do I combine a scalar with a matrix? Very carefully. You really don't, do you? You have to do something, and the something that you can do is you can actually did I change anything in that expression by introducing an identity matrix? This identity matrix is the same size as the A matrix. It's 2 by 2. And the identity matrix has 1s on the diagonal, 0 everywhere else. But S, capital X of S, is the same as S times an identity matrix times capital X of S. But doing that, inserting that I, now allows me to combine SI with this matrix A. So that now I have SI minus A, capital X of S, equaling X of 0 minus plus B U of S. We okay with where that came from. And now what can we do? Now we can actually just divide by this matrix Si minus A, or multiply on the left everywhere by Si minus A inverse to clear Si minus A on the left. Or we're solving now with capital X of S. Capital X of S is now Si minus A inverse X of 0 minus plus Si minus A inverse B u of s. Here, and now we have our Laplace transform of our state vector consisting of two pieces. We have one piece that is influenced by the initial condition on our state vector. If we had an initial position and velocity, we could put that in, and if we inverse Laplace transformed, we would find little x sub 1 of t and little x sub 2 of t evolving based on what the initial condition was equal to. We also have our piece that's due to the forcing function or the input, and that's the piece that's actually going to be more critical when we look at the transfer function. But we just went ahead and kept both pieces just to kind of see the whole derivation in all of its generality. What happens now? Well, we want to try to find the transfer function between u and the output y, where the y is really the position, but we're now playing with matrices. So now let's look at the output equation. And Laplace transform that. We're now Laplace transforming y of t and this one's easy. There's no dynamics involved. We can now simply find or hit the shift key. We now have capital Y of s is equal to c capital X of s plus d capital U of s. And if we replace capital X of s with what we just derived here, we now can write the total solution of our output in terms of initial conditions and forcing function. We now have c times si minus a inverse x of 0 minus plus c si minus a inverse b u of s plus d u of s. And how do we find the transfer function? We neglect initial conditions, and we now can write down what's left over, so that now y of s is c si minus a inverse b. And let me just go ahead and factor out the d times d u of s, and what's in square brackets is our expression for g of s. G of s in terms of state space representation or state space matrices is c si minus a inverse b plus d. If you give me an a, b, c, d, so now in the stadium this weekend when somebody says, give me an a, give me a b, give me a c, give me a d, you can stand up and say, transfer function g of s equals c si minus a inverse b plus d, right? You'll never forget this, hopefully. This will be one of our cheers. So if somebody starts saying, give me an a, you're going to be thinking b, c, d, and now I know what the transfer function is. Right? Now, how do we connect this with our earlier work? Now we simply plug in the appropriate matrices. We have, what was our D matrix? If we go back now to our example, what was D? That was 0, so that piece falls away. And we really end up with G of S is now C, 1, 0, times S, I, minus A, inverse times B. And now you can go home and compute that. You now need to be able to find a 2 by 2 matrix inverse and work on finding that before Wednesday's class. And we'll leave it at that for today. But you already know the answer in the back of the book. Yes? So you know what you should end up with for this particular case.